Hi, so like the previous chapter 15 exam, for the chapter 16 exam, I will be doing number 6. I wrote each part to it as this was multiple choice problems, and I'm actually going to go back to number 6. Okay, so the learning goal states to understand the terms in the Doppler shift formula. The Doppler shift formula gives the frequency f sub L at which a listener L hears the sound emitted by a source S at frequency f sub S. And the equation is stated right here, as stated from the learning goal, where V is the speed of the sound in the medium, V sub L is the velocity of the listener, and V sub S is the velocity of the source. So in part 1, it is asking the velocity of the source is positive if the source is blank. So I'm going based off the equation, the frequency at listener will decrease as the source will move away from the listener. Hence, the velocity of the source will be taken as positive. So really just the larger value of the numerator will decrease the quantity. So if I go back, yep. So the answer is that the velocity of the source is positive if the source is traveling away from the listener. If it's traveling away from the listener. Moving on to part B, it then asks the velocity of the source is measured with respect to, so this just depends really on the distance itself. It doesn't have any respect towards the listener. It's just how the source receives it is really just based on how far away they are from each other. So the velocity of the source is measured with respect to the blank. It's going to be respect to the medium, and also includes, such as air or water. Air being people and water being like sounds emitted in the ocean. As you go down to part C, the velocity of the listener is positive if the listener is blank. Now this is basically just backwards from part A. If the velocity of the listener is taken as the positive, then the frequency given by the listener will be less than the original frequency itself, according to the first formula. So frequency increase when the listener or the source moves towards each other. The velocity itself of the listener being positive, the listener is traveling towards the source. So if like two people walk towards each other as they're talking, it's going towards the source. It's going in that positive direction towards the source instead of having that distance turning away, and now the frequency is much higher. And just like part B above, the velocity of the listener is measured with respect to also the medium. Also depends on just the distance in between the source and the listener. For part E, the full problem states, imagine that the source is to the right of the listener, so that the positive reference direction from the listener to the source is in the positive x direction. If the listener is stationary, what value does f sub L approach as the source's speed approaches the speed of the sound moving towards the right. So this, we can actually use the equation itself. So using the equation itself, we have F sub L is equal to the F sub S of V plus V sub L over V plus Vs. Okay. So since the listener is stationary, that means V sub L is going to be equal to 0. And as the velocity of the source approaches, the velocity of the sound is just going to equal the same velocity. So V sub S is going to equal V as well. So then that changes to the frequency sub S of the velocity plus 0 over velocity plus velocity. That's just going to equal F sub S of V over 2V, which the V's end up canceling out, resulting in 1/2 F sub S. That's going to be our answer for that. All right. Then moving in to part F, it says, now imagine that the source is to the left of the listener, so that the positive reference direction is in the negative x direction. If the source is stationary, what value does F sub L approach as the listener's speed moving in the positive x direction approaches the speed of sound? So since excuse me, so for part F, since the F sub L, and I'm just going to actually write it again, equal to F sub S V plus V sub L over V plus V sub S V. Sorry. It's going to be equal to, so this time what's going to happen is V sub L, or of the listener, is now in the negative direction, and it's going to be equaling the sound of velocity itself. And the velocity of the source is actually just going to equal 0. Well, in that case, frequency sub S, it's going to be times velocity, but it's going to be minus velocity since it's going in the negative x direction, over velocity. Frequency sub S is just going to be 0 over V. Well, 0 over V just equals to 0, and then 0 multiplying F sub S is just going to equal to 0. So that's actually going to be 0. Oh, sorry. That's actually going to be 0. Okay. So then moving on to G, says, in this last case, imagine that the listener is stationary and that the source is moving toward the listener at the speed of sound. So it also says, note that it is irrelevant whether the source is moving to the right or left. So what is F sub L when the sound waves reach the listener? So this time the source is moving towards the listener and the listener is actually stationary. So in that case, we can go F sub L again of F sub S of V plus VL over V plus VS. And now we substitute, so V sub S, or F sub S, it's going to be multiplied by the velocity. At that time, the V sub L is going to be, or the velocity of the listener is going to be 0. He's stationary. It's going to be over, since he's going in the negative x direction, he's going towards the listener. So he's going to end up being V minus V. So you have F sub S of V over 0. So that's undefined. Whenever it's undefined, really you can just cross out any other choices of either 0, 1/2 f sub s or 2 f sub s, it's really just going to approach infinity. It's unknown. We do not know a definitive answer for it, since you are dividing v divided by 0. So that, at the end, the sound waves approaches infinity. And that evidently becomes or creates what is called a sonic boom. You know, the listener will not hear any sound until the sonic boom reaches him or her. So at that instant, the frequency will be infinite. There is no time between passing waves. They are literally right on top of each other. So it's a lot of energy to pass by the listener at once, which explains why a sonic boom is so loud.